Recording in progress.
Yeah, comes on everyone. Let's start off. So last thing we were doing, efficiency of a cycle. Hope everyone has gone through the notes. Perfect. So let's go ahead with a few more questions on this. So the main thing, I hope everyone remembered all these results for each process, the work done, the delta U and everything. Let's go ahead with one more question. Are those cams on? So we got a PV graph here. A, B, and C. This is V naught. This is 4V naught. And gamma for this gas is gamma 1.5. So in this process ABCA, right, we have adiabatic process, isobaric, and isothermal. So first of all, you have to figure out which one is isobaric, which one is adiabatic, and which one is isothermal. So identify the processes.
So is AB a straight line?
Yeah, it's a straight line. Click on isobaric. So, and find the volume at C. Right, and find efficiency of the cycle. Let's get this thing. Get me the volume at C and efficiency. You can figure out the process, that is fine. I'll start removing the people whose cams are not on. So you can rejoin once I kick you out. Did you guys get the volume? Without volume, you won't get efficiency. So I hope everyone figured out the processes. So AB is isobaric. That was the most obvious one. So PC and AC, which one is isothermal and which one is adiabatic? Last class I taught you this. Whoever has more slope, so if you see AC ka slope is this and BC ka slope is this. The one with the steeper slope will be adiabatic. So BC is adiabatic. and Ca is isothermal. There, that would be a CT question. They do ask such things. How do you find volume at C and the efficiency? Try. I'll give you 2 minutes. So if you see the difference, right, in the previous class, what we did, it was like isobaric, isothermal. I'm just bringing different processes. Anyone got the volume? Sorry, AB is isobaric. I wrote isothermal. Shaunak, are you there? Everyone adjust your cams a bit. I can't see you guys. Shaunak, Shreyan, Rudransh. Make sure your faces are visible on the screen. Now see, one thing I'll tell you. Generally, whenever they ask efficiency, right? If you can find or if we can get everything in terms of temperature at A, temperature at B, and temperature at C, right? Basically, you can actually calculate most of the stuff. Okay, so let's start like this. Let the temperature at A be T naught. Let's start like that. I don't know what is that, but let the temperature at A be T naught. Now, if the temperature at A is T naught, what is the temperature at C? That is also T naught, isn't it? Why? Because AC is isothermal. Sure with this. Since AC is isothermal, that is also T naught. What about temperature at AB? So in the process AB, it is an isobaric process. Since an isobaric process, V is proportional to T. So VA by VB is equal to TA by TB. So VA by VB will be V naught by 4 V naught. This will be temperature T naught and this is TB. So temperature at B will be 4 T naught. Perfect. So I literally got all the temperatures here. So temperature at B is equal to 4 T naught. Great. And it is also given gamma is equal to 1.5 and that is nothing but 1 plus 2 by F. This gives you F is equal to 4. This must be some kind of a mixture. It must be some kind of a monatomic and diatomic mixture. That's why you're getting 4. Perfect. So I got the temperature. Now in the process B to C, it's an adiabatic process. Now look at this. I know temperature at B, I know temperature at C, I know volume at B, I want to find volume at C. So in an isobaric process, I need to find a relation between T and V. So I can use TB, VB power gamma minus 1 is equal to TC, VC gamma minus 1. TB is 4 T naught, VB is 4 V naught, gamma minus 1 is half, TC is T naught, and this would be VC power half. T naught will go off and square on both sides. That would be 64 V naught. Check. Any doubts on this? Now, next thing, if you want to find efficiency, what should you do? You should draw the table. So AB, BC, CA, delta U, work done, delta Q. Can you fill up this table? And once you fill up the table, you'll get the total work done and you'll get the positive heat. Efficiency is work done by positive heats. So the story is always the same. I'll just keep changing the processes, but the idea is always the same. There, let's fill up the table. I'll give you a minute or two. I'll do it in the next page more detail. I just drawed it rough. Get the table. Find work done delta U and delta Q for each process. Solve everyone. You know how to find, right? Delta U, you know how to find. You know how to find work done. Just use the formulas and substitute there. So stop playing with the air and start solving. So AB, BC, CA. Delta U, the work done, and delta Q. So I know F is 4. So for A to B, what is delta U? F by 2 nRT. F is 4. N I don't know. N is not given. Okay. R and temperature is 3T naught. TB minus TA. That would be 6 nRT naught. It's an isobaric process. So work done in AB will be NR delta T. That will be 3 nRT naught. Delta U plus W will give you delta Q. That is 9 nRT naught. Perfect. Now B to C. Remember, this is isobaric. This is adiabatic. So if this is adiabatic, this will be 0. C to A is isothermal. If C to A is isothermal, then this is 0. If this is 0, this will be minus 6 nR T naught. Agreed? Why? This total has to be 0, no? The delta U in a cyclic process is 0. And if this is minus 6 nR T naught, then this has to be plus 6 nR T naught. Why? Because delta U plus W is 0. Can you see? Without solving anything for BC, it popped up. And what about C to A? So C to A, the work done will be NR T ln V final by V initial. So this is NR T naught ln. When you go from C to A, this is volume by A by volume at C. That will be ln 1 by 64. Because VC is 64 V naught, and that will be 2 power minus 6. So minus 6 NR T naught ln 2. So this is minus 6 nR T naught ln 2, and this also will be minus 6 nR T naught ln 2. Please have a look at the table. Anyone didn't understand how I got anything, please ask. And the efficiency of a cycle will be total work done by positive heats. The total work done, we have to add all this. That would be 9R T naught minus 6 nR T naught ln 2 by positive heats is only 9R T naught. nRT naught will cancel everywhere. You end up with 3 minus 2 ln 2 by 3. That's your efficiency, everyone. Like I said, once you know the formulas, temperature, you're done. You'll get everything you want. Have a look at this page. Any doubts on this? Let's see one more like this. Any doubts? Anything that you're not convinced here? How did you get the volume or the temperature or anything here? Great. Let's see one more. Let's see one more like this, and I think that should take care of this efficiency thing. Yeah, this was a old JE question, JE 97, 30 years back. This was a 5 marks ka question. Let's get this. So during that time, it used to be subjective. You literally have to write everything, and you get 5 marks for this. They used to give you around 12 questions, 60 marks, 2 hours. Here, there is no graph. You have to draw the graph first of all. That's what makes this question really good. Try. Draw the graph first of all. Read the whole question, draw the graph. Then we will find efficiency. Let's see your reading skills, how you extract data from the question. That's also a very important skill. Okay, let's see the graph. 1 mole of an diatomic gas is taken through a cyclic process starting from A. The process AB, first I'll try to draw roughly, okay? The process AB is an adiabatic process. So AB, it should look something like a curve, but it's an adiabatic compression, okay? So meaning you must have went this way. Volume decreased. Then B to C is an isobaric expansion. Okay, isobaric expansion. So it is like this. Then C to D is an adiabatic compression, something like this. But D2A is isochoric, so that should have been a down vertical line. Matlab A yahan pe nahi, A must have been below this. Make sense? That is how the graph would have looked. So let me draw it properly now. Something like this. So A, B, B to C is isobaric expansion. Then C to D is again adiabatic expansion, and D to A is isochoric. Perfect. Now he also gave some data also. The volume ratios of A, so this was VA and this was VB. That ratio is 16, and VC by VB is 2. And understand VA is also equal to VD, so they both are one and the same. Temperature at A is 300 Kelvin. That is the best thing. If you know temperature, like I said, you can figure out everything. Calculate the temperature of the gas at B and D. Okay. Find the efficiency of the cycle. Find the temperatures and draw the A, B, B, C, C, D. Get the table. Right, Samyak. Temperature at B, you got it right. And here they gave you the values here. 1.6.4, 1 by 8.4. You need them. Drawing the graph itself is a question. Try. Get the temperatures. I'll give you another minute or two. Get the remaining also, Param. What are you waiting for? This is not school. Solve. Get the whole question. You got one answer and you're like feeling happy and you're waiting for it. Keep going. Area, that is wrong. Or maybe you typed it wrong. Area, Shausha. 300 say you went to 5,000. That will be the temperature of the sun outer core surface. So let's see. The volumes are given, and let's start from A to B. A to B is an adiabatic compression. Perfect. I know temperatures, I know volume. So it is straightforward, right? TA VA power gamma minus 1 is equal to TB VB power gamma minus 1. Temperature at A is given 300. Then VA by VB whole power gamma minus 1, and gamma is given 1.4, so that's 0.4 is TB. There's nothing there actually, it's a straightforward equation. And the VA by VB is how much? VA by VB is 16. So that is 300 into 16 to the power of 0.4. And it is given in the question 16 to the power of 0.4 is 3.03. That would be 909 Kelvin. Bas, oh yeah. Why are you guys struggling with this? Nothing there. You just have to apply a formula there. And when you go from B to C, it is an isobaric process. So VB by VC is equal to TB by TC. VB by VC is given as that is half. because that is VC by V2 is 2. TB, I know 909. This is TC. So TC will be 1818 Kelvin. Get temperature at C also. Then we need to find temperature at D. Now CD is again an adiabatic process. TC Vc power gamma minus 1 is TD Vd power gamma minus 1. But I know Vd is equal to Va. So TC is 1818. And this will be Vc by Va whole power gamma minus 1 is 0.4. That would be 1818. Vc by Va is how much? Vc by Va is not there directly. We have to find it. So Va by Vb into Vb by Vc. Va by Vb is 16. Vb by Vc is half. That will come out to be 8. So Va by Vc is 8. This would be 1 by 8 whole power 0.4. There, that is also given 1 by 8. So 0.435 into 1818. Leave it there. That is okay. Just get the table. Don't simplify. Just write the table and you're done. Once you got the temperatures, question is over actually. But please have a look at this. Other than that formulas, I didn't do anything really out of the world. 790, yeah? Okay. So this is something like 790.8 something. So yeah, then yeah, once you're done, I will not just solve the whole thing. I'll just put the formulas. You guys can try later on. So AB is adiabatic, so 0. CD is also adiabatic. CD. That is also 0. DA is isochoric, so this is 0. Yeah. So A to B, you can find that gamma say gamma is 1 plus 2 by F is equal to 1.4. 2 by F is equal to 0.4. 0.2 F is equal to 5. This is a diatomic gas. So what is this thing? Delta U will be F by 2 N R TB minus TA. F by 2 NR TC minus TB. You know all the temperatures we can substitute here. F by 2 NR TD minus TC. F by 2 NR TA minus TD. Perfect. So you got all delta U's. If you got all delta U, so in this process, if you see, the sum must be 0. So this is minus of F by 2 NR TB minus TA. This will be minus F by 2 NR TD minus TC. Perfect. B to C is isobaric process, which is NR delta T, which is TC minus TB. When you add them, BC, this will be simply NCP TC minus TB. D2A is isochoric process, so that will be again F by 2 NR TM minus TD. Perfect. You got everything, so you're done. So efficiency will be add all the work, and I think this will be positive. This guy will come out to be negative. Positive heats. Substitute, you'll get the answers. I'll leave it there. Got the process, right? So getting the graph and then figuring out all those things is there. So it's really not a tough question. It is just a little lengthy. Had to do some work. Any doubts on this? All clear with this? Shreyan? Clear? Vanchika? Srihari? Clear? Devanshi? Aditi? Ovia? Clear? Samyak? Perfect. Next thing. Let's go ahead. So there, that is a little about efficiency of the cycles. Next thing. In a process, dq is equal to du by 2 plus dw by 3. This is a monatomic gas. Find the molar heat capacity of the process. These are another standard main circle questions. Now understand that thermodynamics first law is dq is du plus dw, that is always valid. And he's saying other than that, this is also valid. I think I'll give you a minute. It's an easy one, but yeah, you have to know how to handle it. Okay. How do we get that? Let's see. So we know from first law, dq is equal to du plus dw. This is always valid, right? So dw is dq minus du. Take this and substitute in this equation. Take this and substitute here. So this will be dq du by 2, 1/3 of dq minus du. Bring all dq's to one side. 2 dq by 3. This is du by 6. Then we get dq is equal to du by 4. But what is dq? nc dt. And what is du? ncv dt. Hope you remember that. You're done. So molar head capacity is cv by 4. And what is cv? fr by 2. F is the 1/4 of 3r by 2. 3r by 8. Check. So whenever you get these kind of questions, right, the idea is to eliminate work done, then get dq in terms of du. Now for every process, remember du is what? F by 2 nRT or ncv dt. And what is dq? From calorimetry, dq is nc dt. That is the whole definition. So from there, you'll get a relation directly between c and cv. And then you're done. So this is how you handle them if they give you any other thing. Do have a look at this. Right, Utsa, you got it. Ovia got it. Ishman, right. Right, Aditi. All clear with this? Easy one, not a tough one, but yeah, it's a standard model, so you should know how to handle this. Next one. An ideal gas undergoes adiabatic process where the molar heat capacity Cv is given by A plus Bt. So normally Cv used to be Fr by 2, right? But this is different. This gas is behaving a little different. The Cv is depending on temperature. Higher the temperature, more Cv you get. A and B are constants. So this is some weird process. Even though it's adiabatic, that Cv is not constant. T is the temperature. Find the relation between temperature and volume. You cannot say Tv is equal to gamma minus 1. This is not valid here. That formula was derived under the assumption Cv was Fr by 2, constant. But here Cv is changing. Find relation between temperature and volume. When can you get this kind of situation? This kind of situation, occurs when, think of like this. Let's say we have a compartment, right? And we have, let's say, oxygen molecules, O2. Now, as you increase the temperature, some of the oxygen molecules, right, they will start breaking off and they'll give you atomic oxygen, single O. As temperature rises, molecules dissociate. Into atomic hydrogen. You might think like, okay, how does that change the problem? Think about it. Initially, the F used to be 5. Now it is becoming 6, isn't it? So one oxygen molecule will have a degrees of freedom 5 at low temperature. But two oxygen monatomic things, each will have F is equal to 3 and is equal to F is equal to 3. So that one oxygen molecule ka degrees of freedom became 6. Making sense? As more and molecules are breaking down, the degrees of freedom will keep increasing. So this is a case where their Cv is not constant. So what is Cv? Fr by 2, isn't it? But your F itself is changing. Is that making sense? The F average is changing continuously. So they can actually frame questions like this. They will say like this, assume the number of oxygen atoms dissociating is proportional to temperature. Then you can't take Cv is constant. So now here you have only single oxygen. There will be still some oxygen molecules, okay? It's not like everything has broken down. Now, because of this, F increases. Is this making sense? So this is a kind of a process where Cv will not remain constant. And not only this, this formula Tv power gamma minus 1 is equal to constant. This is derived when Cv was constant. So Cv was Fr by 2. You took F is constant. So be careful here. It's not valid. You cannot use this formula. Exam, they won't tell you all the story. Since Cv is changing. But yeah, this is one way to think like why Cv is changing, why Cv is not a constant. Yeah, Reshman. And remember, it's an ideal gas. So PV is equal to nRT is still valid. That is always there with you. Think it's a good one. Let's see how you handle this. But any doubt in the question, like, anything that you're not clear, please ask. Yeah, let's see. Yeah, this is a little lengthy. Okay, there's a little bit of working on this. Show mate equation. I don't know what is that. So CV is A plus BT, and it is mentioned in the question. It is an adiabatic process. So dq is du plus dw. dq is 0. du is ncv dt. dw is pdv. So pdv is equal to minus n A plus bt dt. And we also have pv is equal to nRT. So pressure is equal to nRT by V. Take this and substitute in this equation. Then you end up with nRT dV by V is equal to minus NA dt minus NV dt. Bring that this side. So dV by V, N will cancel, minus A by R dt by T minus B by R dt. Perfect. Integrate on both sides. This would be ln V minus A by R ln T minus B by R T plus constant. Send that R that side. R ln V plus A ln T is equal to minus Bt plus constant. So R into constant is another constant. This would be ln V power R plus ln T power A is equal to minus D plus constant. This would be V power R, T power A. Exponential will go that side. It will be E power minus D plus constant. Bring the T power minus Bt this side. This will be V power R, T power A, E power plus Bt is equal to constant. There, that's the relation. Options will be like this. This is not any standard process which you see. This is not polytropic, nothing like that. This is completely different weird process. This is how you handle them. Options also will look like this only. Exponential and to the powers. Do have a look at this. It's more of a math. Yeah, only two equations. dq is du plus dw and pv is equal to nRT. Remember this. You don't have anything else. Every question, it's all based on these two only. V is equal to e power raised. Yeah, right, Utsa, you got something like that. I think you got it. You just have to simplify it. Any doubts on this? Let's see. There. So this is another type of model there, but it can be a really good question. Huh? As the gas is heated, it is observed the oxygen atoms, the molecules break down into atomic oxygen. Because of this, the degrees of freedom will increase. So they can make a question around that thing. This is another model. We have a insulated container. We have a piston. This is smooth, massless, movable, adiabatic, or insulated piston. Yeah, there are a lot of things there. So here it is P naught, V naught, T naught, helium gas. P naught, V naught, T naught, helium gas. So both are same. But on the left compartment, there is a heater. So someone switched on the heater for some time. It started releasing heat, and the left side gasket temperature started rising, and it started pushing the right compartment. So something happened. When heater switched on for some time, the pressure in the right compartment increased to becomes 243 by 32 P naught. So the pressure in the right compartment became this much. Find the final temperature of the gases. Both the compartments. And find the heat supplied by the heater. There. This is a good one. This is another variety of questions. Let's see how you approach this. Think. I'll give 2-3 minutes. Did you guys figure out what's happening? Let me give an idea there. So when you draw the picture, the pressure has increased, so the piston must have moved here. We don't know. It must have moved. Always get the data, okay? What do you think will be the pressure? Do you think the pressure will be same in compartments or it will be different? Pressure has to be same. Why? If the pressure is not same, the piston will keep moving, isn't it? Pressure will be P1, P1. That much I know. Let the volume be V1 and let the volume be V2. Let the temperature be T1 and let the temperature be T2. And it is given in the question, P1 is nothing but 243 P naught by 32. Perfect. And we also know V1 plus V2, the total volume is constant, 2 V naught. Make sense? I got all the data here. And gamma is 1 plus 2 by 3. So that is 5 by 3. It's a helium gas. Perfect. Now tell me one thing. If this whole vessel is insulated, piston is insulated, is there any heat going to the second gas? There is no heat transfer to the second gas, isn't it? Therefore, it must be an adiabatic process. The right compartment must be undergoing an adiabatic process because there is no heat going into it. Whatever is coming is all work only. So that is the main thing to realize. Okay, it's an adiabatic compression. Once you got that, then what is the adiabatic process correlation? P1 minus gamma by T power gamma is equal to constant. Why am I using this? Because look at the question. They're talking about pressures and temperatures, isn't it? So yeah, I think I know everything. So initial pressure was P naught. 1 minus gamma, that would be minus 2 by 3. T power gamma, T naught power 5 by 3 is equal to, final thing is 243 P naught by 32 whole power minus 2 by 3, and the final temperature is T2 power 5 by 3. I think you can put a cube on everything. Then this would be P naught power minus 2, T naught power 5. 243 is how much? 3 by 5 and 2 power 5 minus 2 and T2 power 5. That P naught power minus 2 also will go off. We'll end up with T naught power 5. 3 by 2 whole power 5 minus 2 and T2 power 5. That 5 also will go off. Then you end up with T2 is equal to T naught into 3 by 2 whole square. 9 T naught by 4. You can check out the working. Yeah, right, Aditi. Right, Samyak. You guys got the temperature. You forgot the square, Dhyatan. Perfect. Can you find T1? If you see, right, we are just using the formulas only. This is what is it. Unlike mechanics, you really need not think like, oh, that is happening, this is happening. Kuch nahi hai. What process is this? That is the first question you'll ask. Once you know what process it is, you know the formulas for work done, delta U and everything. How do I find the temperature in the first compartment? Think. We'll give you a minute. So how do we find the second one? Look at this. Second one, you already know the temperature of the right compartment, isn't it? So for the right compartment, I can use this P naught V naught by T naught will be 243. Number of moles will remain same by 32. The volume is V2 and temperature is 9 T naught by 4. So from here we will get V2 is equal to, that would be 4 the 8 by 27 V naught. Perfect. Then I'll know V1 from here because V1 will be 2 V naught minus V2. That is 46 V naught by 27. Great. Then from the left compartment, Same thing. Again, with the number of molecules is P naught V naught by T naught. That must be equal to the final pressure, 243 P naught by 32. Volume will be V1, which is and temperature will be T1. So solve this. Take this V1, substitute here. From here, you'll get T1. Got this? I'll leave the working to you. कितना आ रहा है 27/2 क्या? Okay. 3T naught by 2, 27/2. Check it out, whatever it is. Question is still not over. How do you find the heat given by the compartment? No, here, listen to this. This is an important thing. How do you find how much heat the compartment is giving? Now, instead of thinking what is happening, listen to this flow diagram, okay? What is the heater doing? Heater is giving heat. To whom? It is giving heat to the left compartment. And what did the left compartment do? The left compartment took some of the heat and converted it into its own internal energy, delta U1. The remaining energy, it did work on the piston. And what did this piston do? This piston compressed the compartment, right compartment. And in this process, the internal energy of the right compartment increased. So think of like this, Matlab, I really don't know how it is going on, but if I just ask you this question, let's say there is one person here, there is some person here, there are some people here, there are some people here, and so on. There are multiple people, okay? You gave this guy some money. At the end, you realized this person got 10 rupees, this person got 20 rupees, this person got 10 rupees, and this person got 10 rupees. How much money did this guy give? The sum of all this, isn't it? Because whatever these people must have got must have trickled down from all these processes. We don't know how the heat must have transferred, but at the end, everything has become internal energy. Is this making sense? So that means the heat supplied by heater is nothing but the change in internal energy of both the gases. That will be delta U1 plus delta U2, which is nothing but NCV, the difference in temperature, T1 minus T0. You know T1 ka value. NCV T2 minus T0. You know T2 ka value. Substitute here, you'll get the answer. So that is the total heat supplied by the heater. So the heater gave heat to the left compartment. The left compartment stored some of it to increase the temperature. Remaining energy gave it to the piston. The piston took this work and pushed the right compartment. And the right compartment, the heat delta Q is 0, so everything became work. So temperature increased in the right compartment. So the simple story is, end of the day, whatever heat you supplied must have gone into increasing the temperature of both the gases. Is this making sense, everyone? Any doubts on this? Clear? Perfect. Let's see one more like this. If you got this one, I think then you understood this kind of problems. I think this was a whole JE question. I think I don't remember exactly. Let's get this. Sit straight, everyone. Don't lean down. Don't give support your head and everything. Read the question. It's a big one. Read the question. First of all, grasp the data. Don't jump into the problem. Read the data, understand, okay, what is happening with what compartment. Think about it for a minute or two. And then once you got the idea, then draw the final diagram. That's the second part. Get the data. Second thing, draw the final picture. How does the final thing look like? And then you start solving. If you can draw the final picture, that will, yeah, give you most of the data there, idea there. Okay, let's see. So first, let's try to understand the data points in this. The figure shows an insulated cylinder divided into three parts ABC. Piston 1 and 2 are connected by a rigid rod. So now because of that rigid rod, what will happen? The compartment B ka volume can never change. Because this rod in the middle will not let you compress. So you can actually say the B undergoes an isochoric process. Okay. Piston 1 is perfectly conducting. So this piston here is perfectly conducting. And what will the conducting piston do? Because of the conducting piston, temperature in A and B will be always same. Temperature at A is equal to temperature at B due to the conducting piston. Because if the temperature was different, the heat will start flowing through the piston. Great. Compartment A is given heat through the heater and the final volume is 4V0 by 9. Okay. So let me just draw the final picture. So the final picture should look something of this sort. This thing must have moved here. B ka volume will not change. This is this rod. Now see, if this pressure is P1, this pressure is also P1. Do you agree? If the pressure in the compartment 1 and compartment 3 is not same, then the system will keep moving. If this temperature is T1, then this temperature has to be T1 because it's a conducting piston. Right? If this is T1, then this will be T2 and this will be P2. Have a look at the variables. And if you look at the volumes here, this is 4V0 by 9. This is V0 and the total volume is constant. So V0 plus 5V0 by 9, that's 14V0 by 9. This is your heater. Check. This is the first thing, getting the data. So pressure in the first and third will be same. Temperature in the first and second will be same. And then what is given? Volume is given. What do you want to find? You want to find the pressures and the temperature. Perfect. Let's take each compartment. Let's take compartment 1. So this is compartment A, B, and C. Let's start with compartment C. Compartment C, right, is an adiabatic process. Why? That piston is insulated. Look at this. Even though the first piston is conducting, piston 2 is perfectly insulating, meaning heat cannot pass through the piston 2. So this is an adiabatic process. Perfect. Then means I can use initially T naught, V naught power gamma minus 1 will be T2, 4V naught by 9 gamma minus 1. And gamma is given as 1.5. This will be T naught, V naught power half, T2, 4V naught by 9 whole power half. So we end up with T2 is equal to 3T naught by 2. Clear this? And also I can find the pressure now. P naught, V naught by T naught is equal to, pressure is P1, volume is 4V naught by 9, and the temperature is 3T naught by 2. This will give you P1 is equal to 27 P naught by 8. Please have a look at this. So there I got the pressures and the temperatures, P1 and T2. I got these two. You're getting how we are playing around? Can you find the rest? Think. I'll give you a minute. Take a break. Come back by 9:45. We'll continue then after this. Take a 5-minute break and come. Then we'll continue with the problem. Let's continue solving this. Heater is 19 PV by 4. Okay. Cams on, everyone. What else we need to find? Now look at compartment A. P naught, V naught by T naught. The number of moles are constant. The final pressure is P1, 27 P naught by 8, and the volume is 14 V naught by 9 by T1. There, that will give you the temperature also. That is 9.3. 47, that's 21 T naught by 4. T1 भी आ गया. Then for compartment B, I can do the same thing. P naught, V naught by T naught. Pressure is P2. Temperature is same as 21 T naught by 4. Sorry, that's volume. There, you got P2 also from here. Clear with this? There, I found all the pressures. I found all the temperatures. Then what? Find the heat supplied by the heater. Now, let's draw the flow diagram, okay? So whatever heat the heater is giving, so first this will go to compartment 1. And what A will do? A will store some of its internal energy U1, right? And then some of it heat will pass through the piston. And then some of it will go through work through piston. So the heat which went through the piston, what will that do? That will go into the compartment B and that will store the energy there. So that will be delta U2. And what happened to the work on the piston? Now, remember this, when you're pushing the piston, the volume is not compressing here, but the volume in C is getting compressed. So all that energy goes to delta U3. Can you see the flow here? Again, same story. That means end of the day, the total heat provided by the heater must be used to change the internal energy of all the three gases. So the heat supplied is delta U1 plus delta U2 plus delta U3. And what is delta U? F by 2 NR delta T, which you know how to do. Great. And what else am I asking you? The heat supplied by the heater. Great, we got it. Work done by gas in B. That is work done by gas. Work done by gas in A and B. Now, what is the work done by the gas? There is a work done on the piston. That is gas A. That is nothing but delta U3. Because whatever you do work on the piston by gas A, that goes into delta U3. What about work done by gas B? That is 0. It's an isochoric process. Volume is not changing only. What else you want? Heat flowing through the piston? So whatever heat that went through the piston must be change in internal energy. Delta U2. There, you got everything. Please check. So that is your main idea there. You need to understand how the heat cut flow is going on. Once you got that, everything falls in place. It's a pretty good question. Little lengthy, but yeah, doable. Any doubts on this? Perfect. So that's your first law. right? You saw different things, efficiency of a cycle. You saw this, finding the relations between P and V, and then we saw this piston moving, pressures and everything. So these are some models. I hope you can see the difference. Even though the formulas are the same, chemistry or physics में थोड़ा वो difference है. The next thing, second law of thermodynamics. Now, second law is removed from the mains portion, the heat engine part, but it is there for bits, it is there for CET, it is there for advanced, so it is there. Now, unlike chemistry, right, where they focus more on entropy, in physics, we are more interested in heat engines. The first thing is Clausius statement, a bit of a theory there. So what the Clausius statement says is, it is impossible for a machine to transfer heat from a cold reservoir, basically a cold object or a cold system, to a hot reservoir without external work. Meaning, try to understand the statement. Normally, heat flows from high temperature to low temperature. But if you want to take heat from low temperature to high temperature, you need to provide work. Best example, think of a refrigerator. When you use a refrigerator, right, what does a refrigerator do? Or look at your AC, right? What does your AC do? It takes away the heat from your room and it throws out into the atmosphere, meaning you're cooling the room, which is more, it is already cool. You're cooling it more. And in order to do this, you need to provide electricity. So basically, you cannot have a machine which will automatically transfer the heat from low to high temperature. Sorry. Next thing, a heat engine. So the variation of this, working between two temperatures. And like I said, in physics, all processes, right, we take it as reversible only. Because if it is irreversible, pressure and temperature will not be defined till it reaches a steady state. So we will not handle those things. The heat engine working between two temperatures in a reversible process cannot be more efficient than a Carnot engine. We'll see what is a Carnot engine. You must have done and came a bit. More efficient than a Carnot engine working between the same two temperatures. So if your temperature of the source and the sinks are same, and if you have different engines, so this person called Carnot, he somehow figured out, like, that Carnot engine is the thing with the maximum efficiency. We don't have the proof for that, so we'll not get into it. But that is the thing. So a Carnot engine gives you the maximum efficiency. Kelvin-Planck statement. These are all simply another form of, the second law. A heat engine cannot convert all heat into work. So basically it tells you cannot have an engine with 100% efficiency. In a cyclic process. Clear this? There. Now, what is this Carnot cycle? Now, we don't need the derivation. The formula is more important. So Carnot cycle is actually a combination of two adiabatic and two isothermal processes. So just remember that much. A, B, C, and D. So AB is your reversible isothermal expansion. So in this process, the temperature will be T1 and heat Q1. So heat Q1 is absorbed at temperature T1. So the system takes heat from a system of temperature T1 or heat of Q1. Then when you go from B to C, you have a reversible adiabatic expansion. Adiabatic, so there's no heat absorbed in this process. C to D is again reversible isothermal compression. So this would be temperature is T2 and the heat will be Q2. So when you go from C to D, you reject heat Q2 is rejected from the system. At temperature T2. I'll show you how will the net diagram will look like. D to A is reversible adiabatic process. So in this entire cycle, one time you'll take heat, one time you'll reject heat, and other two times you don't take any heat. You just do work. You can actually assume some variables and you can solve this. You can actually find Q1, Q2 ka ratio. We will not get into this, but the main result is this. So that Q1 by Q2 will be the ratio of T1 by T2. You should definitely remember this result in a Carnot cycle. Let's see how to put it in a more usable format. So there is a whole proof on this. We can do that, but we don't need it. So see, this is the thing. So when you have a heat engine, so we have a source. So source is the high temperature one. We have an engine and we have something called a sink. So source is your high temperature. So you take heat Q1 from here at high temperature and then you reject some heat here, Q2. This is your sink. Sink is a low temperature. In this process, you do some work. So think of like this, huh? When you put coal into a steam engine, right? You're burning the coal, right? And whatever heat is released, that is Q1. So the engine will take all the heat Q1. But in this process of boiling that steam, and everything, some steam will escape from the steam engine, some smoke will escape, the heat will radiate, all that is heat rejected, which is Q2. So this is the diagram for a heat engine basically. So you get heat Q1 from the external source and then you do some work and the remaining goes into it gets wasted. So here Q1 must be equal to W plus Q2, energy conservation. So how do you define efficiency? Efficiency is nothing but the work done by the positive heats, which is W by plus Q1. W is nothing but Q1 minus Q2, which is 1 minus Q2 by Q1. And just now we saw from the Carnot cycle, Q2 by Q1 is nothing but T2 by T1. So if this is a Carnot engine, the efficiency is given by 1 minus Q2 by Q1, and this can be written as 1 minus T sink by T source. This is the main formula you need to remember. Questions are pretty straightforward and easy on this. You can put on that formula. This is only for Carnot cycle. If it is any other cycle, then we have to derive the whole thing. But this is the most efficient cycle. But generally, people don't use this. This thing does not generate enough, because see, first of all, a reversible process will take infinite time. You know this? So that is your main formula there. If you, as long as you know that, you'll get the equation. So let me show you some questions on this. It's all based on that one formula there. Yeah, but anyway, I think me and Smith abhi stopped asking. Let's get these two questions. Again, remember, this is the only formula. Efficiency is 1 minus T sink by T source. Let's see. Look at the first one. Efficiency of a heat engine whose sink is at a temperature of 300 Kelvin is 40%. So efficiency is 1 minus T sink by T source. This is the formula. So he's saying the efficiency is 0.4 when the temperature of the sink was 300 Kelvin. So 1 minus 300 by T source. So from here you can find T source. That would be 0.6, 300 by 0.6, that's 500 Kelvin. And then he's saying to increase the efficiency to 60%, that's 0.6. Keeping the sinker temperature constant, so that is 300, and this is your new T source. I'll just call it T new. That would be 300 by 0.4, that's 750 Kelvin. So he's asking how much temperature must it change. So delta T is 250 Kelvin. Bas ho gaya. You really get questions like this in mains and CET. Easy? Get the B part. That looks right, Samir. B part also you got it. Right, Obi, I get the second part. That second one looks wrong. A Carnot engine is operating between temperatures T1 and T2 has efficiency 1 by 6. Now, this is a good one. Huh? The problem with this question is we don't know whether T1 is sink or T2 is sink. They didn't mention who is sink and who is the source. Clear? They simply said T1 and T2. So you had to first figure out who is the sink and who is the source and then start the problem. Because if you take it wrong, you'll get something else. So how do you figure out which one is the sink and which one is the source? Start from there. Think for a minute, then I'll show you. So how do you know which one is T10? A Carnot engine operating between temperatures T1 and T2 has efficiency 1/6. When T2 is lowered by 62, efficiency increases. So ask yourself, 1 minus T sink by T source. When T2 is lowered, suppose if T2 was sink, right? And if you decrease the temperature of the sink, what do you think will happen? If the temperature of the sink decreases, then this whole term will decrease, then the efficiency will increase. Perfect. But if the source ka temperature decreases, then this will increase, then efficiency will also decrease. Making sense? So that is how I know T2 is the sink and not the source. Is that making sense? So if T sink decreases, efficiency increases. So this is a conclusion. Therefore, T2 is sink. Perfect. Then efficiency initially is 1/6, 1 minus T2 by T1. So it's not 1 minus T1 by T2. Its efficiency increases to 1/3 when T2 is lowered by, so that will be 1/3 is equal to 1 minus T2 minus 62 by T1. Done. Two equations, two unknowns. You can solve this. How much did you guys get? 372, 310. Yeah, most of you got the same, right? So from here we'll get T1 will be 372 Kelvin and T2 will be 310 Kelvin. You can solve it and check. Clear with this? So the important thing is to figure out who is the sink and who is the source. Once you got that, then it is just a matter of solving the equations. All sure with this? Let's see something a little better. So that would be a straightforward CET or bits level questions. Let's say we have a coupled engine. So what's a coupled engine? We have two engines in series. So we have a source. We have an engine 1. Then we have a sink. This will also act like a source. Then we have again engine 2. So basically whatever heat is rejected from engine 1, that is used to run the engine 2. They do this in power plants. In thermal power plants, after the steam is generated, the steam which is escaping, they capture that steam, they reheat it and again use it for everything. It increases the efficiency by around 4-5%. So you take heat Q1 from here, you get some work W1, and then you reject some heat Q2, and that heat Q2 is directly passed on to the engine 2, and then engine 2 will give you some work, and then it is passed on to the sink. Again, Q1, Q2, 3s are not given, okay? I'm just showing you. Efficiency of the first engine is N1, and efficiency of the second engine is N2. Find the efficiency of this whole system. Efficiency of engine 1 and 2 is eta 1 and eta 2. So each engine efficiency is eta 1 and eta 2. So you can say engines in series. Find efficiency of this coupled engine or find the efficiency of the system. Answer should come in terms of eta 1, eta 2. So all options will be in terms of eta 1, eta 2. Let's see how will you handle this. How do we handle this? See, again, go back to the basics. What is efficiency by definition? Total work by heat given, isn't it? So what is the total work? W1 plus W2. And what is the heat given? Q1. Any ideas? See. So what is eta 1? So eta 1 is nothing but W1 by Q1. What is eta 2? W2 by Q2. So what is the efficiency of the system? Efficiency of the system is the total work W1 plus W2 by Q1. That is the initial heat given, isn't it? So this can be written as W1 by Q1 plus W2 by Q2. W1 by Q1 is nothing but eta 1. And this can be written as W2 by, W2 by Q1. You can write this thing as W2 by Q2 and Q2 by Q1. That would be eta 1 and that would be eta 2. And what is Q2 by Q1? That is nothing but Q1 minus W1 by Q1. That would be eta 1, eta 2, 1 minus W1 by Q1, which is again eta 1. So you end up with eta 1, eta 2 minus eta 1, eta 2. Check. Right, Samyak. Do you know how this thing looks like? But everyone got this thing, how we did. If you just, we just substituted the things, there's nothing new there. This thing looks like a Venn diagram. If you have studied Venn diagram. So if you have, this is eta 1 and this is eta 2 and this is your intersection. If I ask you what is the area of this Venn diagram, it is eta 1 plus eta 2. So basically this full circle area, this full circle area, but you counted the middle area 2 times. So you have to subtract minus eta 1, eta 2. Do you guys know this Venn diagram? Eta 1 plus eta 2 minus eta 1 union eta 2. Did you guys study something like this Venn diagram somewhere in 10th or maybe in max? Now using the same logic, what if I have 3 engines? If you have engine 1, engine 2, engine 3, can you guess how will the answer look? Then you have a Venn diagram with 3, right? Then what will be the area of this thing? Eta 1 plus eta 2 plus eta 3, but you counted this area in the middle 2 times. So that's minus eta 1, eta 2, minus eta 2, eta 3, and minus eta 1, eta 3. But you removed this middle part, plus eta 1, eta 2, eta 3. Right, Samay. Clear with this? So there, you can play like this, Venn diagram ke saath. If you have 3 engines in a series, this is the efficiency. All clear with this? Right, Utsav. Yeah. All clear with this? Next thing. This is the kind of questions you can expect. Advanced में तो है ये. Let's see one more. So let's say we have a liquid here. So we have a liquid here, mass m, specific heat and temperature is 2T naught. This is your source. So you're taking heat from the source and you're getting some work here. This is your Carnot engine. And you're rejecting to this sink, which is ms T naught. This is your sink. Now tell me one thing, if I remove heat from the system, what will happen to the temperature? It will decrease. If I give heat to the sink, what will happen to the temperature? It will increase. That means here the sink ka temperature and the source ka temperature are not constant. They're changing every instant. If the sink and source ka temperature are changing every instant, that means efficiency is not constant. Eventually, when the sink and source ka temperature becomes equal, heat will stop flowing, efficiency becomes zero. Find the final temperature and the work done. So till now, right, we are taking sink and source ka temperature to be constant. What if they are varying? Let's see how will you handle this. This would be a good advanced one. How do we handle this? How do we handle this? Yeah, S is the specific heat capacity. M is the mass, S is the specific heat capacity. That's your final temperature, Srihari. Dimensions are matching. Does that answer even make sense? So how do we handle this? Again, remember, you cannot use that formula directly there. 3 to root 2. Okay, that looks right, Riyaditi. Let's see. Now, as you are giving out heat, the temperatures will not remain constant. Let the temperatures be T1 and T2. And in this process, let dq1 heat be taken from the system and dq2 heat is rejected from the system. And in this process, you get a small work dW. So this formula Q1 by Q2 is equal to T source by T sink. Right? And efficiency eta is 1 minus T sink by T source. These are valid when the temperature is constant. So what we do here after time t, let temperatures be T1 and T2. In small time dt, since the time is very small, we can assume the temperatures are almost constant. Right? In small time dt, let dq1 heat, right, come from source. And dq2 heat is rejected to the sink. So we can write then dq1 by dq2 will be T sink, T source, that is T1 by T2. This is valid. And we also know dq1 is equal to minus ms dt1. If you remove dt heat, then the temperature will decrease by dt. And why minus? Because temperature is decreasing. Negative since T1 decreases. Similarly, dq2 will be plus ms dt2. Temperature is rising. There, we got all the data there. Now if I substitute here, minus ms dt1 by ms dt2 is equal to T1 by T2. ms will cancel. So dt1 by T1 minus sign is equal to dt2 by T2. Integrate on both sides. Your initial temperature is 2T naught, final temperature is T final. Initial temperature is T naught, final temperature is T final. This will be minus ln T final by 2T naught, ln T final by T naught. Bring both on one side, you'll end up with ln T final square by 2T naught square is equal to 0. Therefore, T final square is equal to 2T naught square. So T final is equal to root 2 T naught. Check. So finally, both the systems ka final temperature becomes root 2 T naught. Then how do you find the work? Ask yourself, whatever is the heat lost by the source, let's say if the source is losing 100 joules and the sink is gaining 40 joules, what happened to the remaining? That must have gone into the work. So heat lost by the source minus heat gained by the sink. The difference must have been the work done. That you can calculate m into s into 2T naught minus root 2T naught. That's your final temperature. This is m into s into root T naught minus T naught. Solve this, we get the answer from there. I think ms T naught 3 minus 2 root 2. Yeah, Aditi got it. Right, Utsa. Got the temperature. Clear with this. So this is the kind of questions you can expect. Every time they won't directly give you the sink and source and finish it off. Clear with this? That's a bit about heat engines. Now in heat engines, there is a one more variation, refrigeration cycle. So refrigeration cycle, right, is reverse of an heat engine. Source, let's say we are using a Carnot engine, and sink. So what we do in a refrigerator, you take heat from the sink. Think of like this, the air condition, right, which you use in the room, that is your heat engine. So AC, the room is your sink, right? For in order to do this, you have to provide some electricity. So you give work, right? And then this is your outdoor unit or your atmosphere. So basically you remove heat from the room, right? And then you remove Q2 heat from the room and you throw it into the atmosphere Q1. Did you ever stood beside a outdoor unit in the AC? You get a very hot air from there. Ever observed it? So where are you getting that from? Basically, all the heat, right, is removed from the room and it is being pushed out. In order for this to happen, you have to provide electricity. So here, because it's a Carnot engine, again, you're using Carnot engine for this. That formula is still valid. Q1 by Q2 is T source by T sink. Now, important thing here, we don't say, efficiency. It doesn't make sense. So there is no efficiency in this thing. So what we say is coefficient of performance. Because in an engine, right, if you want efficiency, you're supposed to get work. Here, you're providing work. So how do you calculate this thing? So how do you remember this? I'll give you an example. You tell me which one is a better AC. I have two ACs, okay? AC1 will take 1 joule of electricity and it will remove 5 joules of heat. AC2 will take 1 joule of electricity and it will remove 8 joules of heat. Which is a better AC? The second AC, right? So that means what you're interested is the amount of heat that you can remove from the room Q2 by the amount of work required, isn't it? How much heat can you remove from the room for a unit electricity? The better this number, beta, the better the efficiency, or you can say the good AC it is. Make sense? So you can define beta as heat rejected by work, which is Q2. Work is nothing but again Q1 minus Q2. So you can substitute here. This will be 1 by Q1 by Q2 minus 1. Substitute T source and T sink. You end up with beta is equal to Q2 by W, which is T sink by T sink minus T source. You should definitely remember this. There have been direct questions. They don't ask you anything more. They'll give you the numbers, put there, and you'll get the answer. This is called coefficient of performance. Exam like CET or bits, you do get. They'll just give you the temperatures and ask you find the coefficient of performance. Clear with this? Now there's a third type. Now this is technically not there in the portion, but this is something which they can frame questions in advance as a paragraph or something. We call it heat pump. Now in India, we really don't hear much about it because this is mostly used in cold countries. So listen to the concept again, an easy concept, not a tough one. So what is a heat pump? So heat pump is reverse of an AC. Or you can say, think of like this. Now, when you go to these cold countries, right, what happens? Outside temperature is -10, -20. So all the houses have to be heated continuously, right? So one way to do, you can get a good heater, right? You send electricity, you get heat. So if you do this, you get 100% efficiency. Meaning for every 1 joule of electricity, you get 1 joule of heat. You can convert all the work into heat. You cannot convert all heat into work. Did you ever thought about this? What is the difference between heat and work? So if you think about that, right? See, this is what I think, heat and work. Work is a superior form of energy. So technically speaking, heat and work both are energy. But work is a high quality form of energy. Think of like this. Iron ore is like heat. It has impurities. Work is like steel or iron, purified iron. Like you remove all the impurities. Getting it? So work is a superior quality form of energy. With work, you can move things. With work, you can heat up things. But with heat, you can only change the temperature. You cannot move things. Making sense? With work, you can do everything, but with heat, you can do only certain things. So work is a superior quality or a better quality form of energy. So this is the idea. Listen, what if you take the AC car outdoor unit and put it in the room and put the AC car indoor unit outside the house? Means you're trying to cool down the earth atmosphere. What do you think will happen? So if you put the AC car outdoor unit inside the room and you're keeping AC car indoor unit outside the room, right? So here, atmosphere, which is already cold, you're trying to cool down the atmosphere even more. So you take heat Q2 from the sink. You have to provide electricity for this. In this process, you reject heat Q1 to the source, the room. Can you see what we can do? We can actually heat up the room better. And see what happens here. So in a heat pump, so what are you more interested in? We are interested in how much heat can you give to the room per unit electricity. We are interested in Q1 by W because you want to heat up the room. So if you go to cold countries, right, Russia or this, European countries, during winters, you'll have this problem. If you go to Britain and all during winters, temperature will go sub-zero. And the biggest problem they have is heating. Right now, the war is happening in Iran, right? Europe doesn't give a shit about it. They have only one problem. The moment right now it is actually happening. Once you hit these Middle East countries, right, the reason they're only worried about is one. If the Middle East countries stop supplying gas, the entire Europe will freeze to death. Getting it? So the only other reliable partner was Russia. But you know what is happening? They're also fighting with them. So the moment the Russia-Ukraine war started, right, the gas prices in Germany, Britain, everywhere went up 4 times. There were some of your senior students, okay? So once when we are talking long back, so someone said like this. Every month they used to get a heating bill, okay? They have something called electricity bill, heating bill, water bill. They have different bills. The heating bill used to come around 200 euros or something per month. When the war started, this bill went up to 800 euros. The room ka rent was like 900 and the heating bill was 800. People were literally bankrupt. Now, this is in a way, India, if you think about this, we don't have a cold ka problem. We have a heat ka problem. But imagine if it becomes too hot and you don't have electricity or AC, what will you do? You'll just open the windows and you'll just sit in some corner, right? You don't die. But imagine temperature drops to -10 and you don't have heating in the house. You'll freeze to death. So having a heat supply is very important for them. So anyway, so how does this heat pump work actually? So Q1 by W. So this is Q1 by Q1 minus Q2. 1 minus Q2 by Q1. So this formula comes out to be T source by T source minus T sink. We don't call it AC actually. They call it a heat pump. Okay, it is designed little differently, but the principle is the same. So just look at the example, okay? So T sink, that means the atmospheric temperature, let's say outside is -23 degrees, which is 250 Kelvin. Temperature of the room, you want to maintain 27 degrees, which is 300 Kelvin. So if I try to use this formula, Q1 by W, you'll end up with 250 by 300 300 minus 250. This is 6. Understand the meaning of this, huh? Q1 is 6W. That means for every 1 joule of electricity, we get 6 joules of heat. 600% efficiency. So if I use that heater directly with a electric heater, right? 1 joule of electricity will give you 1 joule of heat. But if I use a heat pump, 1 joule of this thing will give you 6 joules of heat. Can you see? You get 6 times more electricity. You're actually using it more efficiently. Yeah, 6 is a little big, but in reality, they get almost 2 to 3 times. So this is how they keep their houses warm currently. Previously, they used to use all this, coal and everything burning. So clear with the heat pump? Now, India maybe don't see because our temperature is always high. So yeah, but if you ever go to Kashmir, right, Manali and all this thing, and if you're staying in a hotel, right, look at their, AC unit, okay? It has a dual function. You can cool down the room or you can heat up the room. So it actually works as a both the ways. Anyway, that's a bit about heat pumps. And after this, we have something called entropy. It's a small topic. So next class, when we catch up, we'll continue from here. And then we're almost done. I think it'll take another 20, 25 minutes. And then we'll start off with the heat transfer. That's quite an important chapter for advanced perspective. So that we will catch up on Tuesday. We'll continue there. And do remember, there's a test online. Everyone make sure to give by tomorrow, right? Don't forget to give the test. Okay, with that, we'll wrap up for the day. So do start solving. You can handle most of the questions in thermodynamics now. It's almost done. So any doubts, anything else, please stay back and ask, or else